In this clip, I'm going to be introducing the concept of a basis for the vector space Rn. And by the way, the plural for basis is bases, not bases. Anyway, but before that, I have to introduce another concept, and that is the concept of a spanning set. And it's kind of related to the concept of span that we talked about in a previous clip. And let's start with a specific n. Let's take n equals 3. So we're considering 3D vectors, R3, and I've just listed a few examples of this infinite set, each of them being triples of 3 numbers. And now I'd like to consider a specific set, call it E, containing these 3 vectors, 1, 0, 0, 0, 1, 0, and 0, 0, 1. And I'm going to ask a question. Would it be true to say that every vector in R3 can be written as a linear combination of these 3 vectors? Turns out that the answer is yes, so I'll take an example, the vector 4, 5, 6. If you look, I can write it as 4 times 1, 0, 0, plus 5 times 0, 1, 0, plus 6 times 0, 0, 1. Just a quick computation will show you that this is so. But it's also clear that this can be generalized. I mean, nothing special about 4, 5, 6. And I can replace the 4, 5, 6 by an arbitrary A, B, C and do the same thing. So you see that any vector is a linear combination of these 3. Now, when this happens for a set E, that every vector is a linear combination of it, then we say that the set E spans, in this case R3, and in general it would be Rn. This relates to a previous concept we learned. We learned SP, the span of a set, so we can also write it this way. And now what I want to do is, instead of E, to take a different set of vectors, and I'll call it A. And A consists of 4 vectors, and you probably will notice that the first 3 are exactly what we had in E. But let me ask the same question as I asked before. The question I asked about E, I'm asking the same question about A. If I can write every vector in R3 as a linear combination of the vectors in A. And once again, the answer is yes. Turns out that throwing in extra vectors into a spanning set is not going to hurt, because I can always, well, you'll see from the example. If I take the same vector I took before in the example, 4, 5, 6, we had 4 times this, 5 times this, 6 times this. Now we have this new vector. I can just put 0 in front of it, which shows that adding an extra vector or more than one doesn't hurt the property, because I can always put zeros in front of the extra ones. And just like before, instead of 4, 5, 6, I could generalize it to A, B, C. And so you see that the set A also spans R3, and we can write that the span of A is R3. Okay, so back to the concept of a basis of Rn, and we just talked about the spanning set. I'm getting close to this. And to remind you, we just took a look at 2 sets in R3. Both of them span R3. One of them was E, which was this. One of them was A, which was this. And there is an essential difference between E and A that I'd like to stress. And that difference is that the members of E, the vectors in it, are linearly independent, but the vectors in A are linearly dependent. I think that's fairly clear. One of the definitions of linearly independent is that no one is a linear combination of the others, and I think in this case that's fairly clear. For example, you can't get 0, 0, 1 as a combination of these 2. And similarly, or contrarily, A is linearly dependent, because you can get 1 as a linear combination of the others. For example, this one, 1, 2, 3, is certainly a combination of the first 3, because everything's a combination of the first 3. So This turns out to be an essential difference and leads us to a definition. We're finally coming to the term basis. E spans R3, and so does A, but E is linearly independent. Now, when you have these two properties, that it spans and it's linearly independent, then that makes it a basis. So let me just give a more general definition. And we'll jump from R3 to Rn, because there's nothing special about the number 3, is that if we have a set of vectors from Rn, and you can think of R3, and you can think of this example, it's a basis of Rn if it has the two properties that it spans Rn and it's linearly independent. And in our example, E had these two properties, that it spans R3, linearly independent, so it's a basis for R3. And now let's do an exercise, a typical exercise, to see if we understood. We have a set B, capital B, consisting of these two vectors, and we have to check whether it's a basis of R2 or not. And remember, for a basis we have to check two things. Number one is that B spans R2, and later we'll show that B is linearly independent. The way we show that it spans R2 is that I'm going to show you that if you give me any AB from R2, I can always find an X and a Y, so that AB is a linear combination of these two vectors using X and Y as scalars here. So I have to show you that for every AB I can find a solution XY. So let's multiply the scalars and get this. Next, the addition of these two gives us this. And then from the equality of vectors, it means that they're equal component-wise, and so we get this pair of equations. And the unknowns are X and Y. I'm assuming that AB are given, arbitrary but given. Here we are again. And I'm going to solve it using matrices, although that's not usually the way you would go for such a small system of linear equations. So here's the augmented matrix for this system, and we want to bring it into row echelon form. So what we'll do is subtract twice the first row from the second. If you want it in notation, I would say R2 minus twice R1 goes into R2. In any event, we get the 0 here. Also, don't forget to do the right-hand side to the right of the separator. So here we get B minus 2A. Now back from the matrix to the system of equations. So this is what we get. From the last one, we can easily get y just by dividing by minus 2. And once we've got y, we can substitute in the first equation. And I'll spare you the boring details. X comes out to be this. And if you look back to where x and y came from, we wanted AB as x times this plus y times this. So this is what we get. And this in essence shows us that for any a and b we can find an x and a y, because we can always compute this. There's no zeros in the denominator or anything. Just for instance, if you threw at me the vector 4, 5, I would put a equals 4, b equals 5 here, and if you do the computations, you'll get 1 over minus 2 here and 3 over 2 here. And so it shows you that this 4, 5 is a combination of the two vectors in set B. Another example, minus 1, 2. Similarly, letting a equals minus 1, b equals 2 here gives us this. And you can also even have a double check by just multiplying this out and seeing that this really gives us this. So I think we've demonstrated that these two vectors really do span R2. But remember, there was a part 2 that we also have to show that the set B is linearly independent. One way of showing that these two are linearly independent is to take the equation that a linear combination of this is 0 and show that necessarily the coefficients, the scalars, are both 0, that only the trivial linear combination can give us 0. Well, let's see. Multiply the scalars, do the vector addition, Compare the components, first component, second component. I won't use matrices here, just go ahead and solve it. Subtract twice the first row from the second row. That will give us this. From that we can easily see that y is 0. And if y is 0, plugging that in here gives us that x is 0 also. So the only linear combination that gives the 0 vector is the trivial combination, which means that these two vectors are linearly independent, and we already showed that they span R2, and so they are a basis for R2, and that's the that's the exercise. Now that was an awful lot of work for a simple exercise like that. So here there's a proposition. Proposition is like a mini theorem that's going to help us to do such exercises, and it's going to give us a condition for something to be a basis of Rn. Could be R2, R3, or whatever. What this proposition says is that if I have a set of exactly n linearly independent members of Rn, then it's automatically a basis. There's no need to do the first part of showing that they span Rn. You just have to make sure there's the right number of them. So in our previous example, where we worked quite hard to show that this set, well, it was called B over there, we showed that this was a basis of R2. We showed that they span and they are linearly independent, but we can settle for just showing that these are linearly independent because there's exactly two of them, and this is the 2 from the R2. Like here, we have to show that there's exactly n linearly independent members of Rn, and it's a basis. And another example, say you had the exercise show that this set is a basis of R3. Then if you did it the long way, you'd show that they span R3 and they're linearly independent. But with this proposition, because it's the right number, there's 1, 2, 3 of them, then all we have to do is show that they're linearly independent. And I'll skip that part. I think we've worked hard enough already. It's not difficult to show that they're linearly independent. There's also a corollary, a conclusion from the proposition. And that corollary is that if I have n linearly independent members of Rn, I just say n-dimensional vectors, meaning members of Rn, then they span Rn. And that's because they are a basis. If I have n linearly independent, I should have said members of Rn, same thing, then they're a basis, and because they're a basis, then they also span Rn. There is a companion proposition to this which shows when something is not a basis of Rn, and I want to show you this. And I phrased it in bad English, a sufficient condition to not be a basis of Rn. I just called it for not a basis. And that is, if I have a set of less than n, when I say n-dimensional vectors, I just mean members of Rn, cannot be a basis. So if I have less than n vectors, doesn't matter linearly independent or otherwise, less than n will never be a basis. So for example, if I take the set A, which has just the single vector 3, 4, it will not be a basis of R2 because it has less than 2 members. And another example, this set containing these two three-dimensional vectors will not be a basis of R3 because it has less than 3 members. And next I want to introduce one more concept. There is a very special basis for Rn, and it's called the standard basis of Rn. I'll just demonstrate it on a particular example of n equals 4. The standard basis of R4 is the following set. If you look at it, you see that it always has a 1 and 3 zeros, and the 1 just has different position each time. So 1 with all zeros, there's 4 of these, and that's the same 4 as the R4 because there's 4 places that the 1 can go, and we can generalize, nothing special about 4, and we can generalize this. I just didn't want to write it with ... So I mean, you could get the idea. If I asked you to write the standard basis for R3 or R5 or any other, you would be able to do it. and it would have n members if it was Rn, like standard basis for R3 would have 3 members, 1, 0, 0, 0, 1, 0, and 0, 0, 1, for example. And the final thing for this clip is just want to give you a theorem that will be useful in future, is that there are many possible bases for Rn. There's the standard, but there's many others. But they all have the same number of elements. Every basis of Rn has n members. Okay, that concludes this clip.